Hello students, this lesson is on exponential and logarithmic equations. Solve the following equations for x. Give your answers in both exact and decimal form. So in this first case, we are looking for the value of x that makes this equation true. For a simple equation such as this, sometimes it is sufficient to guess and check mentally. We are looking for an exponent needed on 3 in order to produce 81. Well, 81 factors to 9 and 9. And each 9 is 3 times 3, so we can see that 3 times 3 times 3 times 3 will be 81, so x must be 4. Now if you do not recognize that, then we can always convert to logarithmic form and use a calculator. Recall that if b raised to the c is equal to a, then the exponent c can be written as log base b of a. So in this first problem, if I had simply done this, convert this statement to logarithmic form, it would read the exponent x is equal to log base 3 of 81. And then reach for a calculator, and we get the confirmation of the answer 4. At which point we should have recognized that we could have reasoned our way through this without ever using a logarithm. Yet another approach is to begin with the equation 3 to the x equals 81. I am going to do the log of both sides, where I can choose the base of the log that I'm introducing here. For example, I can do log base 10 of each side. And now I get to use property 8, where I can bring this exponent down as a coefficient. So we have x times log of 3 is equal to log of 81. And now we simply isolate x by dividing by log 3. And then I reach for a calculator and do log 81 divided by log 3, and I get 4. At which point I can recognize I can use property 9 backwards and write this as a single logarithm whose base is 3 and whose argument is 81, and get an answer of 4 still. So there are going to be lots of different methods at our disposal when solving equations where the variable is in the exponent. Looking at this next one, this time the answer is not going to be a convenient number because there is no simple exponent needed on 3 in order to produce 10. So I'll do this by simply converting to log form, and when I do that, I get the exponent x is equal to log base 3 of 10, which gives me a decimal of about 2.096. As an alternate approach, I can begin with the equation and then find the logarithm of each side, and I get to choose whatever logarithm I want. Last time, I chose log base 10. This time I'll choose log base e, or natural log. So find the natural log of each side, then use property 8 that allows me to bring this x down as a coefficient, and now divide both sides by natural log 3. Now you could stop here, or you could recognize that I could do property 9, the change of base property, backwards, and express this as a single log, but of a new base, this time base 3, and of 10. And if I take either of the expressions above and enter them into the calculator, I will confirm that I get about 2.096. So it is acceptable to enter your answer in this form or this form when you are asked to give exact answers, but then if you want to give an approximate answer, use a calculator and give a rounded decimal. And this third one over here, if I simply convert this to log form, I get x must be log base 3 of negative 2. Notice this gives me undefined in my calculator. That's because the argument of a logarithm must be a positive number. We cannot do logarithms of negative numbers or logarithms of 0. And that's because the output of an exponential must also be positive, not 0 or negative. 3 raised to a number cannot produce 0 or a negative result. So this equation is not possible. And you think of this graphically, the graph of y equals 3 to the x is always above the x-axis, and y equals negative 2 is below the x-axis. So there will never be a value of x that will allow me to get a negative 2 result. So we have no solution here. And you want to train yourself to recognize these situations. Okay, let's go to the next page. Solve the following equations for x. Give your answers in both exact and decimal form. All right, for this first one, I do see an exponential statement right here. Now these parentheses around it are super important. If you don't have them, then this expression can be confusing. It might be interpreted as 24 raised to the x. So you want to make a dot very clear right there. But then sometimes students mistakenly say this is 8 to the x, which is a mistake as well. Order of operations does not allow you to multiply the 2 and the 4 first, and then raise that to the x. So it's safe to keep that 4 to the x in its own set of parentheses. Now what I'm going to do here is isolate it. I'm going to begin by adding 1 to both sides, and now divide that 2. And then from here, we have it set up much like the problems on the last page. You can simply convert to log form, and this will produce the exponent x is equal to log base 4 of 9 halves, which gives me about 1.085. Okay, this next one. Notice the next two are the same. I'm going to show you two very different looking strategies for solving this next equation. The complicating factor is the fact that there's x's in two different exponents. So simply converting this statement to a log form maybe won't be very productive. So I'll begin by finding a logarithm of both sides, and I'll use the natural log again. So we have natural log of 3 raised to the 1 minus x equals natural log of 4 raised to the 2x. Now you'd be able to use property 8 to bring this entire exponent down here as a coefficient, and this entire exponent down as a coefficient. Now in this first case, make sure the exponent is in parentheses, because the natural log 3 will then need to distribute, and this is equal to 2x natural log 4. In fact, I'm now going to take this natural log of 3 and distribute it across these parentheses. So 1 times natural log 3 is just natural log 3, minus x times natural log 3, and this is equal to 2x natural log 4. And now observe we have x's still in two locations, but they are no longer parts of exponents. So I need to gather all the terms on one side of the equation that have x, so I can either add this term to the other side or subtract this term to the other side, but I'll choose to add this term here to the right side of the equation. That gives me natural log of 3 is equal to 2x times natural log of 4 plus x times natural log 3. And now the x terms are on the same side of the equation, and every term that doesn't have x is on the other side of the equation. So factoring comes next. I'm going to factor that common x out, leaving 2 times natural log 4 plus a natural log 3. And now everything here in parentheses I'm going to divide to the other side of the equation. So in the end, we get that x must be the natural log of 3 divided by 2 natural log 4 plus natural log 3. And x is successfully isolated, and we can now reach for a calculator to find a decimal approximation. And we get approximately 0.284. Now I solved this using natural log as a logarithm of choice, but I could have began this with log base 10s, in which case every single red logarithm you see here would be instead an log. But as you can see, that does not change the result. We still get about 0.284. So it doesn't matter which logarithm you use here at the very start, as long as they're both the same. Okay, now another very different approach. First, recall some rules about exponents. If ever you have a to a power times a to a different power, so the bases are the same, you can add the powers. If you have a to a power divided by a to a different power, where the bases are still the same, you can subtract the powers. And if you have a to a power, and then you raise all that to another power, you multiply the powers. To illustrate all of these, x squared times x cubed would be x to the fifth. X to the fifth divided by x squared would be x cubed. Subtract the powers. And x squared, and then you cube it, would become x to the sixth. Now I'm going to use these properties, but backwards. So this left-hand side of my equation can be rewritten as 3 to the 1 divided by 3 to the x. And the right-hand side of my equation can be written as 4 squared and then to the x. So this gives me 3 over 3 to the x must be equal to 16 to the x. Now I will multiply the 3 to the x to the other side. So some more properties of exponents. If you have a to a power times a different base but to the same power, you can multiply the bases and then raise to that power. Or if you have a to a power divided by b to a power, you can divide the bases and then raise to that power. So using these ideas, we can write this as 3 is equal to, and then multiply 3 and 16 and get 48, and that's being raised to the x. And now I will convert to log form, and we have our answer. X equals log base 48 of 3. And as you can see, log base 48 of 3 gives us the same answer. These are two very different methods for solving this equation, but they do produce the same final answer, although the two exact forms look very different. So I'm going to take a moment to show why these two versions of the answer are in fact the same. First thing, notice this 2 right here in front of a logarithm. I'm going to use property 8 and bring that up as a power on that 4. And 4 squared is 16, so we get this expression. Now I'm going to use property 6 on these two natural logs being added together and multiply the arguments. And 16 times 3 is 48. And I'm going to use property 9 backwards because I have a natural log divided by a natural log, so I can write this as a new log with base 48 and argument 3. And thus we see that the two answers are in fact the same. It does not matter to me which solution approach you choose to take, but I do recommend you practice both. Okay, next slide. On this page, we will solve 3 different equations, but this time we are solving for x where x is an argument or part of an argument of one or more logarithms. In this first case, x is part of an argument of a log. In such a case, we begin by isolating the logarithm, so I'd recommend first dividing by 3, giving us log of 5x is equal to negative 4/3. Now keep in mind that this logarithm has no base written, so it is base 10. And now I'm going to convert to exponential form. So we do the base b raised to this exponent would be equal to 5x. And then the final step is to divide by 5. Now be careful that you don't simplify 10 over 5 and say 2 to the negative 4/3, because the 10 has a power on it, but the 5 does not. However, I could write this as 1 over 5 times 10 to the positive 4/3, and we could manipulate this even further, but I will choose to stop right here. However, at this point, we can notice that this is a positive value, and it is approximately 0.00928, confirming that this is a positive number. Now, this is important to establish because in the original equation, our variable x is part of an argument of a logarithm. And in previous lessons, we talked about the necessity that the argument of a logarithm be positive, so not 0 or not negative. And for 5x to be positive, that means that x itself must be positive. Only positive answers would be acceptable in this equation, and we have found a positive answer. Now, as an alternate way to begin this equation, in order to isolate the logarithm, we had to remove this 3, and I chose to divide both sides by 3 to isolate the logarithm. But you can also use a log property where this 3 is brought up using property 8 as an exponent on the 5x. So that would give me log of 5x cubed, where 5x cubed is the new argument, is equal to negative 4. And now I will convert this to exponential form. So again, this logarithm has a base 10, so it would be 10 raised to the minus 4 is equal to 5x parentheses cubed. Now my next goal would be to isolate the x. So I would do a cube root next, which really means find the 1/3 power of each side. And the rule here, if you have 10 to a power and then raised to another power, is that you multiply these two powers. So that would give me 10 to the negative 4/3 is equal to 5x. Which is exactly what we arrived at when I took the approach of dividing by 3 first, instead of moving the 3 up as an exponent. So I won't continue this path. Just wanted to show you an alternate first step. Now in this next example, we have x in 2 different arguments of logs, and both of these logs are log base 2. And furthermore, they're being added together. So my goal here will be to express this in terms of a single log that I can then convert to exponential form. If I use property 6, that would allow me to write the left side as log base 2 of a new argument, where my new argument is the product of this argument and this argument. So that would be x times, and then use parentheses, x minus 2, and then equal 3. Now I have a single log statement where the logarithm is isolated. And so I can convert now to exponential form, and that would give me 2 raised to the 3 is equal to this argument of x times x minus 2. 2 cubed is 8, and if I distribute the x, I get x squared minus 2x. This is a quadratic equation, so I'm going to subtract 8 to get a 0 on one side, and then attempt to factor the quadratic equation and potentially get multiple answers. So I need 2 numbers that multiply to negative 8 but add to negative 2. Those numbers are negative 4 and 2. And now I set each factor equal to 0, and I get 2 answers, 4 and negative 2. Now we must test both of these answers against the domain of the original equation. This logarithm in the original equation has an argument of x, and arguments must be positive. Well, this argument also involves x, so I know that x minus 2 needs to be positive. In other words, x has to be more than 2. So of these 2 restrictions, the second one here is more restrictive. If x is more than 2, then not only will this argument be positive, but so will this one. But if x is more than 0 but not more than 2, such as 1, then this argument will be positive, but this one will be negative. And so x equals 1 is not in the domain of this equation. So any viable answer in this must be more than 2. Well, this second option here, minus 2, if you were to try to plug it into the original equation, it would cause negative arguments of logs. So it must be eliminated as an answer. So the only viable answer here is positive 4. So we're seeing that there's a burden on us that we need to check our answers against the domain of the original equation when we are solving logarithmic equations, where the variables are parts of arguments of logs. We did not have this burden when solving an exponential equation where the variable was an exponent, because exponents can be any number. In this third example, I see x's in one argument and in a second argument, both of natural logs. I'll begin by subtracting this natural log from the right side to the left side of the equation. Now I will use property 7. When you have 2 like-based logarithms being subtracted, then we can condense this into a single natural log, and my new argument will be first argument divided by the second argument. Now keep in mind that natural log does have a base of e, and now that the logarithm is isolated, I can convert to exponential form. This would give us e squared must be equal to the argument x plus 3 over x. Now I need to solve this equation for x. Well, I'll begin by multiplying both sides of the equation by x, gathering the x terms on one side, so I'll subtract x from both sides of the equation, factor x out, and then divide. Now we must check this answer against the domain of the original. The fact that we have an argument x right here in this natural log tells us that x should be positive, but then we have another argument here, x plus 3, so that should be positive, which means x itself should be more than negative 3. Now of these 2 restrictions, x being positive is more restrictive. So we need all of our answers to be positive if they are to be valid answers to this logarithmic equation. Without reaching for a calculator, we know that this answer will be positive because e squared is more than 1. But as instructed, let's go ahead and find its decimal representation. And we get about 0.470, confirming that this is a valid answer to our logarithmic equation. Having looked at these three examples, be careful that you don't just assume that any negative x value you find should be eliminated. You must always test all your proposed solutions against the domains of the original equations. In other words, make sure that none of your solutions cause negative arguments or zero arguments of logarithms. Okay, let's go to the next page. Use technology to solve each equation. Now, technology will be necessary in both these cases because here we have x that's an argument of a logarithm and then a free-floating x. It will not be possible to gather the x's in such a way that x can be isolated. So instead, what I will do is solve this equation by graphing each side of the equation as if it was its own function and looking for points of intersection. So in this first case, let's call 3 log x the function f of x and 4 minus x the function g of x. Then I'll graph both these functions in Desmos. Here are our two functions graphed. Click on either graph and you will be able to find its point of intersection. Focus on the x-coordinate. This will be our solution to the equation, and in this case, only one solution. X should be about 2.704. So here's a recreation of our graph, giving us a solution of about 2.704. In the next equation, we have x's in exponents and x's as bases of powers. In this case, it will also not be possible to isolate x in a productive way. So similarly, I will graph the two functions. Click on either graph and highlight the points of intersection. This time we see 2. Copying those graphs here into my work and focusing only on the x-coordinates, and we have 2 approximate solutions. Okay, going on to the next page. Find the inverse function of each one-to-one function. F of x is a one-to-one function. We'll confirm that visually in just a moment, but to find the inverse, I'd begin by changing f of x to y, and then I begin the process of solving this for x. I'm going to add this term from the right to the left side and subtract y from left to right side. That gives me 2 to the x minus 1 is equal to 3 minus y, and now I will convert to log form. So we know that the exponent, x minus 1, will be equal to log base 2, and its argument will be 3 minus y. And now we just have to add 1 to both sides to get x isolated. This is our inverse function using y as the input variable. If I type either of the orange equations into Desmos, these will produce the same graph because they represent the same relationship between x and y. It's just that in this expression, it's y that's isolated, and in this expression, it's x that's isolated. However, if you take either of these equations and actually switch the xy coordinates, you will get these green equations. These green equations, when typed into Desmos, will also give you the same graph as each other, but not the same graph as either of the orange equations. Let's look at both real fast. Here's the first orange equation. Here's the second orange equation. They are the same, so I can just make them both orange. This is a one-to-one function. We'll pass both the vertical and horizontal line test. Take the two orange equations, copy them, but then switch the x and y coordinates. Switching the x and y coordinates of the first orange equation, I get this green equation. Notice it is different. The orange and the green are symmetric about this diagonal line y equals x. Take the second orange equation and switch the x's and y's, gives me this blue equation. And notice the blue and orange are also symmetric about the line y equals x. And notice that the blue and green are the same. Here's the green, here's the blue. So I can make them both green and just reveal one of them. In either orange equation and either green equation, the green and the orange graphs are symmetric about the line y equals x. As far as an answer here, this inverse function rule will be adequate. F inverse of y equals 1 plus log base 2 of 3 minus y. Also acceptable would be the same rule, but with any input variable you technically want. So both w, and this is still the inverse function rule. Both z, and this is still the inverse function rule. Even if both x, this is still the inverse function rule. But I will leave the input variable in terms of y. Now in the case of g, this will be a one-to-one function. Take the g of x, change it to y, and now let's solve for the x. So I will subtract 2, and now that the logarithm is isolated, I will convert to exponential form. This log has a base e, so we know that e raised to the y minus 2 will be equal to the argument 3x. So x will be equal to 1/3 of e to the y minus 2. So this is our g inverse function with y as the input variable. And by way of review of domain and range, the domain of f, look to this rule, x is part of an exponent, and exponents can be any real number. So the domain is all real numbers. This will be the range of the inverse function. The range of f, well, this function, 2 to the x minus 1, has a range of y being positive, reflect around the x-axis, and then shift up 3, gives me a range of negative infinity up to 3. And these are the outputs of f. Well, this will be equal to the domain of f inverse. Looking at f inverse, y is the input variable. There's a logarithm, its argument must be positive, so y itself must be less than 3. In the inverse function notation, y was an input. So the inputs of the inverse function must be less than 3, confirming that the domain of the inverse function must be numbers less than 3. For g function, the domain, x is part of an argument of a log, it must be positive. Multiplying by 3 does a horizontal compression, so x must still be positive, and then shift up 2. That has no effect on the domain. So we know that only positive inputs are allowed in g, which means that only positive outputs can be produced by g inverse. The range of the g function will be all real numbers, which will be equal to the domain of the g inverse function. This was to remind you, as discussed in a previous lesson, that domain and range switch when you compare a function with its inverse. Okay, and this concludes our lesson on solving both exponential and logarithmic equations.